Colin Russell is a model scientist. He is totally enraptured by the beauty of the scientific process. For him, only the rational approach to a problem leads to true solutions. Or, to quote Nobel Prize winner Max Perutz, in science, the truth always wins. Colin has been granted the highly prestigious position of Royal Society University Research Fellow at Cambridge University. This fellowship comes with only one obligation or better, with one prerogative, to devote 8 years to fundamental scientific research. Colin's interest in the evolution and spread of viruses often takes him to faraway countries like India and China, where he was the first to demonstrate that all seasonal influenza viruses originate in Southeast Asia. Yet, Colin firmly believes science should be put to the benefit of mankind. He is devoted to public health and actively contributes to the work of the World Health Organization in many ways. After all, as a young science student, Colin secretly hoped to once be able to save the world, and he still does.
It's not the strongest species that survives, nor the most intelligent, but the one most responsive to change. Now, it sounds like something that Darwin would have said, and it's famously attributed to Darwin many times over, but it was actually said by a guy that you've never heard of from a little university in the United States that you've probably also never heard of. But it does very nicely sum up one of Darwin's key points, which is those things that can survive change are the most likely to survive in the long term. Now, this can be said for plants, this can be said for animals, it can be said for bacteria, and it can especially be said for viruses. And in the case of viruses, it's not the virus that kills the fastest or the ones that spread the most quickly that we need to be concerned about. It's the ones that are most responsive to change. For a virus, survival is really about finding the next host. And viruses have evolved a number of different strategies in order to maximize their opportunities to get to the next host. So let's take rabies as an example. Rabies really does some remarkable things inside every host that it infects. So the first thing that rabies does, so an infected animal will bite another animal, or a human. And after that animal gets bitten, the viruses migrate along the nervous system until it gets to the spinal cord, and then when it gets to the spinal cord, it migrates up into the brain. And when it gets to the brain, it does two great things. Well, great for the virus, not for us. Once it's in the brain, the virus starts replicating like crazy in the portion of the brain that controls that animal's interaction with other animals. And basically what it does is it makes the host paranoid. And so for a disease that's spread through biting, like rabies, making your host paranoid is probably the most powerful thing you can do, because all of a sudden that animal wants to bite everything that it sees. And the other thing that the virus does is that it makes its host afraid of water. Now, at first, that might not seem like a great thing to do until you recognize that actually makes the saliva thicker. And when your saliva gets thicker, you can have more virus in every drop. And that's what gives a rabid animal, or a rabid anything, that sort of foamy mouth appearance. That's just a whole lot of extremely virus-laden saliva right around its mouth. So we now have an animal that's biting everything that it sees, and it's got virus everywhere. It's a remarkable evolutionary strategy. It's literally altered its host behavior to make it transmit more efficiently. Now, there's another thing that's really interesting about rabies as well, and that is the dynamics in different species. So if we look at the dynamics of rabies in raccoons, for example, raccoons are really, really common in the northeastern United States. There's millions of them, they're everywhere. And so in this particular circumstance, it doesn't really matter how fast the virus kills a raccoon, because there's so many other raccoons around that all it has to do is turn its head and bite something next to it, and the disease has survived. It's infected another host. But if we contrast this situation with that for Arctic foxes, for example, rabies infects Arctic foxes in exactly the same way that it infects raccoons. Spread by biting. It takes an infected individual to bite another Arctic fox. But the difference between foxes and raccoons is that there's just not that many Arctic foxes out there. They live in sparsely populated areas. And so if the virus killed an Arctic fox really fast, it wouldn't have the opportunity to infect another host. The virus would kill itself off very, very quickly. And so, in fact, what we see in Arctic foxes is that the virus actually kills Arctic foxes more slowly than it kills raccoons. Now, part of that is probably down to the difference in body size. Rabies tends to kill bigger animals more slowly. But part of it also reflects the host adaptation that the virus has taken on in order to be able to transmit more efficiently and to survive in the long term. Now, one of the things that's interesting about rabies along these lines, though, is that if you get rabies and you survive, well, you'd be really, really unlucky to ever get it twice anyways, but you would probably be immune to future rabies infection at that point. So basically, rabies' strategy for long-term survival is be really, really good at transmitting to new hosts. Now, if we compare that to influenza, though, influenza actually does something different. So influenza has evolved the capability to infect us many times over the course of our lives. And it does this by actually changing the proteins on the surface of the virus, such that after a year or a few years, our body won't recognize those viruses as being the same anymore, and we get sick all over again. But because the virus is able to change these proteins so rapidly, it's part of the reason why the recommendation is that people get vaccinated every year, because the vaccine has to be updated almost every year to keep pace with the evolution of the virus. Now, one of the things that's really interesting about flu is that it's primarily a wintertime disease. You don't hear very much about people getting flu in the middle of the summer. Where do influenza viruses come from every winter? If they're disappearing over the summer, they have to be going somewhere. How do we manage to get them to come back every winter? Because we have epidemics of flu every year. It's been a mystery for a long time. I mean, in the 1940s, people were writing papers about how influenza viruses migrated around the world, and they did this and they did that. And people had come up with a lot of different hypotheses to explain how this might be happening. So one hypothesis was that influenza just circulates in big cities in between epidemics. Everywhere else in Belgium, for example, influenza viruses, as soon as winter is over, would go away. They would just die off. They would go extinct. They wouldn't be finding new hosts to infect anymore. But maybe in big cities like Brussels, the virus would be occasionally finding enough hosts just to be able to sort of trickle along over the summer until the winter came along again and could then flare up and cause a big epidemic. That's one hypothesis. It was very popular. Another hypothesis is that influenza viruses come out of the tropics. And because influenza is mainly a wintertime disease, and there's no winter in the tropics, maybe influenza viruses just circulate there all the time, and thus they could act as this big reservoir of viruses for the northern and southern hemispheres. Alternatively, many people thought, well, actually, there's no winter in the tropics, so there's probably no flu there either. And instead, influenza viruses move back and forth between the northern and southern hemispheres, owing to the differences in the timing of the seasons. Because, of course, when it's winter here, it's summer down there, and vice versa. And yet another hypothesis was that influenza viruses come from China. Why China? Well, why not? They're far away and easy to blame. But the diversity of hypotheses really just speaks to the fact that no one had enough information to know which of those hypotheses was right. But we do know now that all of those hypotheses are wrong. And in fact, we know that each year, influenza viruses all over the world come from East and Southeast Asia. Now, the question is, why East and Southeast Asia? And there's really three reasons why. So one, there's a lot of people in East and Southeast Asia. Billions, practically a third of the world's population lives in Southeast Asia. So we have a lot of people to be infected all the time. Now, the second reason is it's really easy to get from anywhere in East and Southeast Asia to anywhere else in East and Southeast Asia. You can get on a plane in Tokyo and be in Bangkok in 2 hours. It's just not a big deal. But the third element is the really crucial bit, which is influenza is a seasonal infection. And influenza viruses go extinct when winter is over. And so, given that influenza viruses don't continuously circulate anywhere, how is it that they could do it in East and Southeast Asia? We've got the people, we've got the ability to get everywhere, but what about having epidemics at different times of year? And it turns out that the environment plays a huge role in that. So one of the things that sort of came out of all of this work was a better understanding of the dynamics of influenza in the tropics. So it turns out that in the tropics, there's tons of flu. And it's seasonal, just like everywhere else in the world, except There's still no winter, so when does it happen? It turns out it happens during the rainy season. Here again, why the rainy season? Why the winter? Not well understood, but we have a clear seasonal driver of epidemics. And what we see is that in East and Southeast Asia, there are places that are really close to each other, like Bangkok and Kuala Lumpur, for example, only 1,000 kilometers apart, but have their influenza epidemics at completely different times of year. They have their rainy seasons at completely different times of year. So it's a partial explanation of what might be going on. So basically, if you sum up all of the epidemics that are happening somewhere in East and Southeast Asia, at any time of year, somewhere in East and Southeast Asia, there's an influenza epidemic going on. Now, for better or for worse, this unfortunately doesn't tell us anything about pandemics. We have this great big worldwide epidemic of a new disease that has been introduced into the human population from animals. And the thing about seasonal flu is that seasonal flu is always in humans. There's no interaction with the animal population. And whenever we do get a new influenza virus in from humans, it's a subject for big concern. So, all influenza viruses originate in birds. So all of the viruses we've been talking about so far entered the human population from birds in 1968. It was the big Asian pandemic of the time. However, the fact that it was from birds in Asia in 1968 is only a coincidence with what we know about seasonal flu. The two things are absolutely unrelated to each other. And this is especially true if we look at what happened in 2009 when we had the big swine flu pandemic. It wasn't birds and it wasn't Asia, it was pigs in Mexico. Now, in late 2008, you would have had a really hard time convincing anybody who was handing out money for influenza research that you should be focusing more energy on pigs in Mexico than birds in Asia. But there you go. Pandemics really can start anywhere. And that's the thing, the birds in Asia are still a major subject for concern, and we're still very much concerned about bird flu, probably more concerned about bird flu now than we were in 2008. It's still a very real risk. But the real take-home message here is that pandemics start wherever we get a human-animal interface. That can be a farmer working on his farm, it can be a hunter out shooting and collecting ducks, it can be a guy sharing his house with his chickens. And this brings us to one of the sort of classic stories of how people get bird flu. Here we have the case of the Thai duck farmer. Thai duck farmer, one of his ducks, has got bird flu. It's got a runny nose, and he really wants to help. He can tell the duck is suffering. But how do you get a duck to blow its nose? Well, you can help. That's not necessarily a good thing. So what the farmer does is he takes the duck by the head and he puts the duck's beak in his mouth. Not an easy thing to do all by itself. But then he blows. A couple of things happen here. So one, duck's nose cleared, no problem. Other thing that happens, duck's nose cleared, straight into the farmer's eyes. Not only is that gross, it's unfortunate in this particular case because it turns out that's actually a viable route for getting an avian virus, a bird flu virus, into your body. So normally, we have to get a bird flu virus deep into our lungs in order to cause a severe infection. However, an alternate, not easy, but a slightly easier route, is to get the virus into our eyes. And in that case, it typically won't kill us, but you certainly get a very nasty infection. In the case of the Thai duck farmer, it worked out less well. But all of this is really just to say that pandemics can start anywhere. And I can't really emphasize it enough. Pandemics can start anywhere. They can start any time. And new diseases can spread exceptionally quickly, especially when we don't know what we're looking for. So, for example, tonight, before you all came in, one of the people in the audience had their hands coated in UV paint. And to give you an example of how fast the disease might spread in a theater like this, this guy here in front, he's got some nice paint on his face. And all of that is really just to say that in a crowded situation with a new disease, it could spread exceptionally quickly. Thanks very much.